Good day, good day, good day, good day. A warm afternoon to everyone. A warm afternoon to everyone. Welcome to Yebo Tutor. Today, it's a beautiful day that God has made again and given us an opportunity to be able to see today. It's such a great honor. Today, we'll be doing Euclidean geometry, grade 11. So, today, we'll be doing Euclidean geometry, grade 11 stuff, grade 11 work. So now, before we start it, I want us to have this clear image of what really goes on, or what really happens when we are talking about Euclidean geometry. If you are new, please don't forget to subscribe on our YouTube channel. Please also don't forget to subscribe. Don't forget to hit the notification bell so that whenever we are live, you can be notified about our sessions. Also, you can join our WhatsApp group, Yebo Tutor. Then you'll be also assisted when you have questions. You can ask. Then you can be definitely assisted. You can also join our Facebook account, our Facebook page, which is also Yebo Tutor. Also, don't forget to ask questions on the comment section, and let's have an interaction a process so that you can assist each other in the process. So now, Euclidean geometry, let me start it from grade 8, but I want to just highlight the most important things which we'll be looking at from grade 8 and grade 9 and grade 10 before we go to grade 11 work. Now, I want to introduce something that in grade 8, grade 9, we were taught about straight lines. Let's start with straight lines. We have straight lines. So a straight line is a line which is straight. That's a straight line. So let's just say maybe it's AB, from point A to point AB. This is a straight line. It can be like this. It can be like this. It can be like, oh, those are straight lines. Okay. Now, according to the Euclidean geometry now, according to the basics and the idea behind Euclidean geometry, we have some reasoning which we have to do. Why are we saying this is this angle? Because of this certain reason. We must be able, we are doing a reasoning here. We do something, then we answer why we are doing it. So we must be able to write our reason. Always don't forget to write your reason. So let's now start with the straight line. So a straight line, let me just say straight line AB, it adds up to 180 degrees. So angles, then now let me just say this is the first dot, then we'll say A. So maybe, for instance, we are having this straight line, then we are having this A and B. So we can definitely say, if they ask you to calculate A or B, you have to say that A plus B is equal to 180 degrees. Why are you saying that? Because angles on a straight line, angles on a straight line. Okay, that's the entire reason. Angles on a straight line are supplementary. So when we're saying angles on a straight line are supplementary, we're trying to say that all the angles which are on a straight line, they add up, or they produce, or they give us 180 degrees. Even if we are having things like many divisions, we're having many divisions. You have A, B, C, D. When we add all of them, they still have to give us 180 degrees because they are on a straight line. So all angles, when we add all of the angles, they must give us 180 degrees on a straight line. Then after that, we must know that on a straight line, on these straight lines, we have what we call parallel lines. We have parallel lines. Parallel lines are lines that will never meet. They can be like this. They can be like this. These are all parallel lines. As long as they never meet, those are parallel lines. So there are certain things which are important about parallel straight lines. So when you're talking about parallel lines, parallel straight lines, for instance, that is the first thing which we want to talk about. So if we have two parallel lines like this, then we have a transverse line, which is this one. This angle is always equal to this angle. Okay. All right. This angle is always equal to this angle. Why? Because provided that AB is parallel to CD, these two angles are equal. Why? When they form an F shape, when parallel lines form an F shape, these two angles are always equal. When parallel lines form an F shape, these two are always equal. So what's the reason? The reason that, let's just say this is 1 and 2, this is 1. So A1 will be equal to angle C2. What's the reason behind that? It is because they are corresponding angles. Then you have to state the parallel lines. If you don't state, your answer will be void. You have to state that these are the parallel lines in which you are saying that these two angles are corresponding angles. So these are our corresponding angles, provided that these two parallel lines are there and they are connected with a transverse line forming an F shape. So when we are having an F shape, those two angles, they are always corresponding to each other. So when we have an F shape, always know that these two angles are corresponding angles because they are the same, they have the same answer. Now let me just write here that they form an F shape. Now number 2, we have what we call alternating angles. So when we talk about alternating angles, when we are having, for instance, we are having these parallel lines which are like this, then we have this transverse line like this. These two will be equal to each other. These two will be equal to each other. Why? Because they are alternating angles. So angles which are formed by a Z, this Z, these two angles are equal. This Z, these two angles are also equal. So alternating angles are formed with the letter Z. Then in the last one, we have what we call co-interior angles. So when we're talking about co-interior angles now, co-interior angles, for instance, we are having these two parallel lines attached with the transverse line. Let me just say A, B, C, D. This one, these are co-interior angles. When you add these two, co-interior angles are supplementary, which means they add up to 180 degrees. So these two angles, when you add these two angles, they must give you 180 degrees. Why? Because they are co-interior angles, provided that AB is parallel to CD. So even you guys, please don't forget to write the parallel lines. That will give us the correct answer. That will enable us to know what you are writing about. Okay, let me just draw this one now. These are two parallel lines. AB is parallel to CD, having a transverse line, which is, let's say we are having a transverse line, which is like this. Then here maybe we say we have E, here we say we have D. Then we say we have 1, 2, 3, 4. We have 1, 2, 3, 4. Then now we say this is our E. So having this line now let's apply all the things which I've just said right now. So what the first thing which you're gonna see here is that we can see that firstly we say that angles on a straight line add up to 180 degrees, which means these two angles, when you add them, they give you 180 degrees. When these two angles, you add them, they have to give you 180 degrees. When you add D1 plus D2, they must give you 180 degrees. Why? Because they are angles on a straight line. 3 plus D3 plus D4 is also equal to 180 degrees. Why? Because they are angles on a straight line. Now, looking in this side now, D3 plus D1 is equal to 180 degrees. They are angles on a straight line. D4 plus D2, they are equal to 180 degrees. They are also angles on a straight line. Then E3 plus E1 is equal to 180 degrees because they are also angles on a straight line. Then E2 plus E4, they are equal to 180 degrees. They are also angles on a straight line. So we are done with talking about straight lines now. Always know that all angles which you see on a straight line, they add up to 180 degrees. They are supplementary angles. Now, let's go to the next one now. We've spoken about these two lines being parallel. Then we say that we have what we call corresponding angles. So now let's look on the corresponding angles now. We say that the corresponding angles, they form an F shape. So let's look now on the instant which you are having here. This is an F shape. So we say that if this is an F shape, we say that this angle and this angle will correspond to each other. So E4 is equal to D4. Why? They are corresponding angles. They are forming a F shape. Also this side again, E3 and D3, they are also corresponding angles because they are forming their own F. So these two, they are equal to these two are equal to each other because they are corresponding angles. Then now, also, if we are looking from above, coming from this side, when we are coming from this side, let's use this one. I want something different. Let's use this one. If you are coming from this side now, this is the transverse line. We are looking at it from upwards. This is also an F. So if this is an F, which means D2 is equal to E2. They are also corresponding angles. And also on the other side as well, D1 is equal to E1. They are also corresponding angles. So always know that the corresponding angles are formed when the parallel lines join with the transverse line and form an F. It's always the case that when that happens, that is what we have. Now, moving forward now, let's remove this. Okay, let's remove it. Okay. Okay, now we are done talking about corresponding angles. Now let's talk about the angles which form a Z. So this Z, we say the four angles which form a Z, they are called alternating angle. So D6 and these ones, they are alternating to each other. Also, this one, when you are looking from this side now, this one and this one are also forming their own Z because they are alternating angles. So alternating angles are formed when lines are corresponding to each other. They are forming a Z shape to each other. Now, moving from alternating angles, we have what we call the co-interior angles. Now, the last one. The co-interior angles, we say that the co-interior angles are supplementary. So E3 plus D5, E3, let me just do this. These two angles, when you add them, they must give you 180 degrees because they are co-interior angles. Co-interior angles are always supplementary. In other words, they add up to 180 degrees. So all supplementary angles, all co-interior angles, they add up to 180 degrees. Now, the last thing which I want to mention also on parallel lines, it's so important that you know these characteristics as I'm saying them because sometimes they'll ask you to prove when you're writing a question. Okay, now let's say now continue also having our transverse line. We still have our 1, 2, 3, 4, 5, 6, 7, 8. Okay, we say this is D, this is E. We have what we call vertically opposite angles. So vertical opposite angles, they are the angles which are vertically opposite to each other. So what's happening here is that E4 is equal to E1. These are vertically opposite angles. So for instance, we are having this X. So these two angles here, they are vertically opposite to each other, because this one is when the two straight lines meet and they cross like this, they form this angle and this angle. They are vertically opposite to each other. This one and this one also, they are vertically opposite to each other. So you must always know that having an X like this, these two are vertical opposite to each other. These two are vertical opposite to each other. So those angles are equal to each other. So now I'm done talking about the parallel lines. Now let's go to triangles. We did this in grade 9, grade 10. This is so essential in the building basis of our grade 11. Now, having a triangle ABC. So angle A plus angle B plus angle C, it's always equal to 180 degrees. A triangle is a supplementary triangle. All the angles of a triangle, they add up to 180 degrees. So you write that angle A plus angle B plus angle C is always equal to 180 degrees. Why are you saying that? So in Euclidean geometry, always when you state that this angle is equal to this what is equivalent to this, we have to state a reason why you are saying that, so that we can be able to see and realize and understand. So there's always a mark for your answer and your reasoning. You must be able to reason to why you are saying this. Okay, so we're saying in this triangle ABC, angle A plus angle B plus angle C, it's equal to 180 degrees. Why are you saying that? Because there are some of angles of a triangle. We are done with the first one. Now let's look at the second one. The second one, a triangle, there are three types of triangle. We have an isosceles triangle, we have an equilateral triangle, we also have the scalene triangle. The equilateral triangle is the one which have equal sides and equal angles. So when all the angles are equal, all angles A, B, C, when all the angles are equal, and when all the sides are equal. So if here it's X, so everything is X inside. That's an equilateral triangle. So all the angles of an equilateral triangle, they are equal, and all the sides of an equilateral triangle are equal. So if here it's Y, everything it's Y. Those are the characteristics of an equilateral triangle. That's the first triangle, the type of triangle which you're talking about. Then now, going to the second one, we have what we call a isosceles triangle. And in the Euclidean geometry, isosceles triangle is so important, it's so essential, because there are two reasons which we come up with after we notice that this is an isosceles triangle. An isosceles triangle, two sides, two opposite sides, which means these two sides, they are always equal to each other. These two sides, they are always equal to each other. So these two sides I'm showing right now to you. Let me just do this so that you don't... Okay, these two sides are equal to each other, but this one is not equal. So when these two sides are equal to each other, they have this nice reasoning which we have to be able to write. So now what happens is that when these two sides are equal, that definitely shows that this angle and this, the base angles, are always equal to each other when these two adjacent sides are equal to each other. So now if AC is equal to AB, always know that angle A is equal to angle B. What's the reason? Angles opposite equal sides. So this is a nice and awesome reason. An isosceles triangle is a nice reason which we must always know and apply. Okay, so we are saying that if we are given triangle ABC and we know and we are told that this is an isosceles triangle, or maybe they just show that this is X and also this is X, which means that AC and BC, they are equivalent to each other and they are also equivalent to X. So now we can now conclude and say that if these two sides are equal to each other, if these two adjacent sides are equal to each other, which means this is an isosceles triangle, and we know that the base angles of an isosceles triangle are equal. So what do we say now? We just say if AC is equal to BC, angle A is equal to angle B, which means the base angles are equal to each other. What is the reason why you're saying that? It's angles opposite equal sides. If maybe they say prove that AC is equal to BC, you just have to, if you know that angle A is equal to angle B, you can prove it easily like that. If angle A is equal to angle B, then after that, if these two angles are equal to each other, then now we can conclude that AC is equal to, BC. If angle A is equal to angle B, we can conclude that AC is equal to BC. But now the reason are just a slight change. So now we can conclude therefore AC is equal to BC. What's the reason now? And side opposite equal angles. Okay, so they are just a reciprocal of each other. So since earlier we say that if we are given that these two sides are equal, that automatically shows that, or that automatically says that the base angles of that isosceles triangle, they are equivalent to each other. And the reason is that angles opposite equal sides. Then moving to the last one now, we say that if now they say prove that AC is equal to BC, you just have to prove that these two base angles are equal to each other. Then when these two base angles are equal to each other, then that's when you can conclude and say, no, AC is equal to BC. Why is that? Because sides opposite equal angles. So that's an isosceles triangle. Then we have a scalene triangle. This is the last one. It's not that important, but just for purposes for you to know. A scalene triangle is a triangle with no equal sides, with no angle. So in other words, it's just this kind of a triangle. It's the black sheep of the family. It's the triangle with nothing which is equal. Everything is just different. Angles are different. We are having X, Y, and Z. All angles inside, they are different. All the sides are different. Everything is not equivalent to each other. That is an isosceles triangle. So this was an overview of our grade 8 and 9 and 10 work. Now we are going to something which we did now in grade 11. Now this is now what we this is when we are now introduced to theorems. So we have 7 theorems which you have to know by heart when you are going to write your exam. You have to know these 7 theorems by heart. You have to know them by your mind with everything which we have. You have to know these seven theorems. All right. So introducing the theorems now. The first theorem, Theorem One. You must be able to prove these theorems. Theorem 1, Theorem 4, Theorem 5 and 7. Theorem 1, 3, 5 and 7. Those 4 you must be able to prove them and prove the reason what we are saying about them. Okay, now theorem now. We have theorem number 1 in Euclidean geometry grade 11. We were told, now let me just write something like this table so that we can help each other using this table. All right, good. Then let's say Theorem 1. Okay. Theorem 1, that's our first one. Theorem 1. So on Theorem 1, what does Theorem 1 state? Theorem 1 always states that a line drawn from the center of a circle. Okay, let's draw a circle first. This is our circle. This is our nice, awesome circle. Okay, mine is a bit ugly, but I know yours will be a bit beautiful. Okay, so a line which is drawn from the center. So a circle always have its center. So a line which is drawn from the center perpendicular to the chord. Let me do something before we go to the theorems. Let me just do something quick. Let me do something quick because to introduce to the terminology so that you can get used to the terminology which is used here. We have to get used to the terminology. Okay. So the terminology, let me start by the terminology first. So we are having, this is our triangle, this is our circle, and the circle always have its center. And we know that this is a diameter, a line which joins from circumference to the circumference, from circumference to the circumference through the center. It's called the diameter. Then a line which is drawn from the center to the circumference is called the radius. This is the diameter. This is called the radius. Any line which is drawn from the center of the circle to the circumference is called the radius. Then this small portion is called an arc. We have this which is called an arc. Then maybe we have this straight line which is here. Let's say maybe it's AB. It is also having this point, maybe P here. This APB is called the tangent. This is a tangent, and these are the important things which you have to know. We have codes. Let's say, for instance, we are having this. This is called a segment, and here we have a chord. So these are the terminology which you have to understand. An arc, it is a part of the circumference. So an arc is basically just this part, or just this part. This small part of the circumference is called an arc. Then the next one, we have what we call a chord. A chord is a straight line which joins an arc. So these two arcs, when we join these two arcs, we have a chord. Then a radius is, we say the radius is a line which is drawn from the center to the circumference of a circle. So even from this center to the circumference, this is a radius, this is a radius, this is a radius. So a line from drawn from the center to the circumference is always the radius. Then we have a segment. We say that a segment is a part of a circle that is cut off by the chord. Then we have the tangent. The tangent is a line. This is the straight line which makes a contact with a circle at only one point. When they meet one point, that's the tangent. Okay, now let's go to the theorems. Now at least you have an idea of what's really going on. Okay, so let's start with Theorem 1. We say that on Theorem 1, let me draw my circle first. I think I'm going to also prove Theorem 1 so that you can see and understand it. Okay. Theorem 1. Okay. Theorem 1. Theorem 1 states that a line, this is our center because the circle always have a center. A line drawn from the center of the circle perpendicular to the chord. We say the chord is it's a line which is drawn, a straight line which is drawn from an arc to an arc. So an arc, we said an arc, it's a small portion of a circle. So these two, let's just say this is our arc. This is our arc. This is our arc. Then we draw this line. Okay. Now, so a line drawn from the center and it joins the arc, the chord, sorry, which is, let me just restart this. Okay. So a line drawn from the center of a circle perpendicular to the chord. It bisects the chord. So what are we saying that? Let's say A, P, and B. Perpendicular, which means they are 90 degrees. Okay. So what do we mean? When we say the line drawn from the center of the circle perpendicular to the chord, it bisects the chord. That's the reason. So a line drawn from the center of the circle perpendicular to the chord. So in other words, let's say we are having the center O. So the line OP is perpendicular to AB. So a line drawn from the center perpendicular to the chord bisects the chord. That's the theorem number 1. So when we are saying that it bisects the chord, which means it divides into two equal parts, it bisects the chord. So if we're having this circle, let's just say this is equal to, which means these sides are equal to each other. They are equal to each other because a line drawn from the center of a circle perpendicular to the chord bisects the chord. So when it bisects, which means it's able to divide the line into two equal parts. That's our theorem number 1. Then we have theorem number 2, which is converse of theorem 1. So the converse theorem, which is the theorem number 2, it says that the line joining the center of a circle to the midpoint of a chord is perpendicular to the chord. But it's not that important. You must be able just to apply it. Then we have theorem number 3. Theorem number 3, just write theorem number 3. This one is a bit important. So theorem number 3, we are talking about circles here. We have our chord and we have our center. Then we say that these two angles are equal to each other, perpendicular bisector. Then we extend that like this. So theorem number 3 states that the perpendicular bisector of a chord passes through the center of the circle. So the perpendicular bisector, let me just do this. The perpendicular bisector of a chord passes through from the center. You see? It's going from the center. It is proceeding from the center. So a line. Okay. So now, theorem number 3 says that the perpendicular bisector of a chord passes through the center of the circle. So in other words, we are trying to say, maybe let's say that this is our C, this is our O, this is our A, this is our P, this is our B. We are trying to say that AP is equal to BP. Okay. And CP is parallel to, so it's perpendicular to AB. So when they are perpendicular, we are talking about theorem number 3. We are having that the perpendicular bisector of a chord passes through the center of a circle. Now, theorem number 4. This one is so much important. This one is examinable. You must be able to prove theorem number 4. Theorem number 4, it's so important. Please make it a point that you try by all means. So let's say we are having our circle, which is like this. Mine is not good, but okay, come on. All right, then. So theorem 4 says that the angle at a center is twice the angle at the circumference, subtended by the same arc. So the angle at a center. So in other words, this angle, please look carefully. This theorem is so important. The angle at a center, let's just say this is O1, this is O2. Okay, the angle at the center, which is O1. O1 is the angle at the center. It is twice the angle at the circumference. So this is the angle at the center. It is twice. It is twice the angle at the circumference. So theorem number 4 is so important that this angle from the center to is twice the angle at the circumference. So the reason which you write in this one, you can just write angle at center is equal to 2 angle at circumference. This is the reason at circumference. So in other words, angle O1 is equal to 2p, angle P. Angle O1 is equal to 2p. So we are saying that angle at the center is equal to 2 times 2 times angle at a circumference. Okay. So that's the reason it's so important that you understand it. If we want to look at clearly, you can see that this, when we join these two angles will be equal to each other, which means that an isosceles triangle. Why? Because a line joining from the center to the circumference, it's a radius, and the line from the center to the radius is also a radius, which means these two lines are equal. So if these two lines are equal, which means these base angles are equal. So if these base angles are equal, what's the reason? Since AB AO is equal to OB and they are both right, we can now conclude that angle A is equal to angle B, angle opposite equal sides. Have your reason always, you write your reason as well so that you can be able to understand clearly. Now, let's now move to theorem number 5. So now on theorem number 5 is not that hard. It's also important. Theorem number 5, it's your circle again. Then there is this thing. Come on now. Okay, let's try to draw it in this sense. Okay. Okay. Then okay. So what's happening here? We're having A, B, C, and D. Angle C is equal to angle D. What's the reason? Angles from the same segment. We say that a segment is this line. This line is the segment here. We can see that these two lines at the circumference, they are coming from the same segment. So we are saying that angle C is equal to angle D. Why? Because they are angles coming from the same segment. You can see that they're coming from the same segment. Line AB is producing this two angles. So angle C is equal to angle D. What's the reason? You have to write the reason always that angles in same segment. Segment. So that's the reason for theorem number 5. Always know that that is our reason. Then we have theorem number 6. So theorem number 6. Now on theorem number 6, now we are talking about what we call cyclic quads. Now we are talking about what we call cyclic quads. Okay. So when we're talking about cyclic quads now, it's so important. It's so much important. Let's say we are having this again. We have these two lines and we have this small line and these two join here. We have A, B, C, and D. So what's happening here is that on a cyclic quad, these are called cyclic quadrilateral. So these two angles, they got 180 degrees. When you add this angle and this angle, they must give you 180 degrees. When you add this angle and this angle, they must give you 180 degrees. So what's your reason now? So in other words, C plus D is equal to 180 degrees. A plus B is also equal to 180 degrees. So what will you say as your reason? Your reason is that you just have to say that opposite angles of cyclic quad. So the opposite angles of a cyclic quad are always equal to 180 degrees. Then there is also what we call we have an exterior angle of a cyclic quad is always equal to the interior opposite angle. So in other words, we are having this as our cyclic quad. I didn't draw it properly. Let me just draw this and say A, B, 1, 2, C, and D. So now we can join the triangle, the circle now. Can join the circle. Mine is ugly, but yeah, I tried to make it a little bit so that you can see. So this angle is always equal to the opposite one. What's the reason behind that? It's because an exterior angle of a cyclic quad is equal to the opposite interior angle. So you can write that exterior angle is equal to opposite interior angle. Okay, then the last one, which is so nice, which I love the most, it's the last theorem, which is called the Tan Chord Theorem. The Tan Chord Theorem, the tangent chord theorem. That's the nice one. But before we go to that one, let's go to theorem number 7. Theorem number 7, when we are having this is our circle, then there are these two lines, having these two lines. Let's say we are having P here, we're having Q and S. So now these are called the tangent from the same point. These are called the tangent from the same points because they are coming from the same point P. So in other words, this is our S, this is our Q. So in other words, PS is equal to QP. Why? Because they are tangents from the same point. Bear in mind that we say a tangent line, it's a line that touches the circle at one point. They have the same coordinate at this one point. So we're saying that these two lines are equal. Why are they equal? Because they are tangents coming from the same point. So you can just write the reason that tangents from common point, from same point. Then the last theorem of the day is the last one, which is so nice, and it's so nice also to apply as well. So on this theorem now, we are given this our tangent here, A, P, and B. So if we have on our tangent now, I want us to draw it in this way, that this angle is equal to this angle. Okay, let me just write it in this form. Okay, then I also maybe construct lines. Constructing lines, then I also construct a different line, then I also construct the same line. Okay, so let's say we're having D, E. So what's happening is that this angle is equal to this angle. Okay, let me just draw this straight line here so that everyone can see. Okay, according to Tan Chord Theorem. Okay, according to Tan Chord Theorem, this is important to know that this chord gives us, so this angle is equal to this angle. Looking at this one now, this one, and this is the chord DP, and let's go with where it's gonna end. This is the chord and this is the line, so it's gonna end up going to where it has to go. Okay, so this is what we have, guys. Please always know that this theorem is so much important. This theorem is so much important. So the reason is that we are saying that this angle is equal to this one. It's because they are it's called Tan Chord. You can just write Tan Chord Theorem as your reason. So that's the reasoning which you can write there. Okay, now let's now move forward now to the last part. Now we are done with the theorems which I wanted us to do today. So the first one, which said it's important, is theorem number 1. A line drawn from the center of a circle perpendicular to the chord bisects the chord. That's theorem number 1. Then we have theorem number 2, which is the converse, and we have theorem number 3, which says that the angles at a center is twice the angle at a circumference. Theorem number 4, the converse is the converse of theorem number 3. Theorem number 5, we said we have what we call cyclic quads. In cyclic quads, we have to understand one thing about cyclic quads. The cyclic quads, we say that the opposite angles of a cyclic quad, they are equal to 180 degrees. In other words, they are supplementary. So if they are supplementary, it actually means that they add up to 180 degrees. So when you write your reason, you just write that they are opposite angles of a cyclic quad. They are opposite angles of a cyclic quad. Okay, now let's move forward now and do questions. Let's just do 1 or 2 questions, then we can summarize our class today. All right, great. Now, having question 9. Let's look at question 9 and do question 9. Let's do question 9. Let's do question 9, 10, and maybe 11. We do also 12. Then we are done. We do this and we are done. Okay. In the diagram below, O is the center of the circle. Point T lies on the chord RS. Prove the theorem which says that OT is perpendicular to RTS, and then RT is equal to TS, which means we have to prove theorem number 1. Let me prove the theorem number 1 for you. So when you are proving that, you must always draw it so that you can be able to understand what you are talking about. So you can draw it, and when you are drawing it, you must always know that it's not that let's just draw it. Oh my word, mine is not good. Yeah, that's better. We have R, we have S, then they said here we have T. And let's do this. Okay, this is our T. 90 degrees. We are given that, and we are given that it's 1 and 2. Okay, this is our T. So this is our O. So what do we do first? You write that we first construct these different things. We first construct the radius to connect these two. So that's what you're gonna write first, né? So we're gonna write that construction of radii. Then now, now let's go now. OR is equivalent to OS. That's first thing. OR is equivalent to OS. OR is equivalent to OS. What's the reason? It's because they are both radii. So when it's 1, it's radius. When they are more than 1, it's called radii. So it's called radii. Then maybe let's just say here, before we write this, let's take the true triangles which we are looking at the similarity. Let's say in triangle or TS and in triangle or TR. Okay, in these two triangles, we have to understand that OR is equal to OR. Sorry, OR is equal to OS. OR is equal to OS. What's the reason? They are both radii. We say that radii is a line which joins from the center to the circumference of the circle. And also we see that OT is common. It is common in both triangles. And also we can see that T1 is equal to T2 is equal to 90 degrees. We know that, and we say that angles on a straight line, they add up to 180 degrees. So since this one we are given that is 90 degrees, so 90 plus 90 is equal to 180 degrees, or T1 plus T2 is equal to 180 degrees. Why? Because they are angles on a straight line. So T1 plus T2, they must give us 180 degrees. So since we have T2 to be 90 degrees, we can make T1 to be the sublet of the formula, and we end up having T1 to be also equal to 90 degrees. So now what is our reason? Our reason is that angles on straight line. Okay, Then now we can now conclude that triangle OTR is congruent to triangle ORS. Then now we can now say that therefore RT is equivalent to TS, sorry. Or TS. Okay. So then we can conclude that this is, so that's how you prove the first theorem. You first, by construction of the radii, which is OR and OS, you construct them. Then after that you say in now O triangle OTS and in triangle OTR. Then now we are now proving it. You want to see by showing the similarity in the two triangles, and we saw that OR in this other triangle is equal to that OS of another triangle. Why? Because they are radii, lines joined from the center of the circle to the circumference. It's called a radii. Then we also saw that OT is common in both triangles, because when we separate these two triangles, OT is also going to be there in the both triangles simultaneously. Then T1 is equal to T2. We say that since we are given that T2 is 90 degrees, so we know that if T2 is 90 degrees, so T1 plus T2 is always equal to 180 degrees. Why? Angles on a straight line. Now, making T1 the subject of the formula is going to be T1 is going to 180 degrees minus T2. What is our T2? Our T2 is 90 degrees. So it's 180 degrees minus 90 degrees, which is equal to 90 degrees. So we are saying that T1 is equivalent to T2 is equivalent to 90 degrees because they are angles on a straight line. Then now, therefore, we can now conclude, because we have looked at everything, then now we can conclude that RT is equal to TS. If you have any question, please do ask. Okay. Now let's move forward. Let's move forward now. Let's look at number 9.2. 9.2. So on 9.2 now, we are given that shape. Let's just read together. In diagram, O is the center of the circle ABD. Where is ABD? Okay, ABD. Okay. The F is the point on the chord AB, such that DOF is perpendicular to AB. This is a perpendicular bisector, theorem number 2. You can just see it. From now, you can just see that, no, this is theorem number 2, and you know what you are supposed to apply. Then we are given that AB, where is AB? AB, okay, is equal to FD. AB is equal to FD. They are both equal to 8 centimeters. Then you're given that OF is X centimeters. Now determine the length of the radius of the circle. What is our radius? Our radius is OB, and we can construct another one which is OA. So now how are we going to determine the radius of the circle? So that's going to be easy. So we know that AF is equal to FB. Always know that. Okay. Okay, now let's write the correct answer now. AF is equal to, let me just show you again so that you can see. Okay, AF is equal to FB. These two sides are equal to each other. So we're going to divide 8 by 2 because these two are equal to each other. Then we end up having AF equal to FB equal to 4 centimeters. Why are we getting 4 centimeters? Because AB is equal to 8 centimeters. So AF is equal to, so these two are equal, so maybe they are X and X. So we can just say that AF is equal, if these two are equal, which means it's just X squared, sorry. And we know that AB is equivalent to AF plus FB. So we say this is X and this is X. So AB will be equal to 2X because they are the same. So what is our AB? Our AB is 8. Then we have 2X. Then we divide by 2. We divide by 2. Then we ended up having our X to be equivalent to 4. So this is where we are getting our AF to be 4. But now you have to write a reason why you are saying that AF is equal to FB. So what is the reason why we are saying that these two are equal to each other? We can write that line from the center line from the center, it's perpendicular to the chord. Don't forget that. It's perpendicular. Line from the center is perpendicular to the chord. So line from the center is perpendicular to the chord. That's why those two are equal to each other. Okay. OD, it's a line from the center to the circumference. So OD is equal to OB. Okay. OD is equal to OB. Okay, which is equal to 8 minus x. Because bear in mind that let me just do this first. Okay, 8 minus x, because the reason it's radi. So in this shape, we were told that OF is x centimeters, and we're also told that FD, it's 8 centimeters. So if this is 8 centimeters, so this OF plus OD, they must give us 8 centimeters. So x plus OD is equal to 8 centimeters. Then we make OD the subject of the formula. So making it the subject of the formula will mean that OD will be equal to the line FD minus OF. And FD, it's 8 centimeters minus x. Then we're going to get our OD to be equal to OB to be equal to 8 minus x. What's the reason? It's called the radi. Now, we know that according to the Pythagoras theorem, now at least we know the value of OB. We know the value of OF. We also know the value of FB. So now we can use the Pythagoras theorem that says OB squared is equal to OF squared plus FB squared. So what is our OB? Our OB is 8 minus x all squared is equal to OF, it's x squared plus, what is our FB? Our FB is 4. It's 4 squared. Then we know that when we expand this, it's going to be, we have already done solving for x. Sorry. So we say that we're going to use the Pythagoras theorem. Since now we know the values of OB and OF and FP. So now we're going to end up substituting them. Then now we can solve this. We have solved, we can expand this. We know that from solving for x. So we're going to end up having 64 minus 8 times 8, 64, 8, negative 16 plus x squared is equal to x squared plus 16. Okay. All right. So we can see that x squared minus x squared is equal to 0. Let's group like terms. Let me just say, let's group like terms. Okay. So 64 minus 16 is equal to 60. Let me just say x squared minus x squared plus 16x. So we transpose x squared to the right and negative 16x to the right. Then this is 0. Then this 64 minus 16, it's 48. Yes, 48. Then we are left with 16x. Then we divide both sides by 16 so that you can get the value of x. Then our x will be equal to 16 into 48. We know that it goes 16, 32, 48. It goes 3 times. So the value of x is equal to 3. But we want the value of the rad. We say that initially that OD is equal to OB is equal to 8 minus x. So now we know the value of x. So now we can determine our rad. Maybe we can just say OB will be equal to 8 minus x, which is equal to 5 centimeters. So basically our OB, our rad is equal to 5 centimeters. It's equal to 5 centimeters. Oh, we're not given units. So if you're not given units, we have supposed to write units. So firstly, we saw that AF is equal to FB, and we divide AB into 2 so that we can get equal, and it's 4, 4. Then we said there is a line from the center perpendicular to the chord. Then now OD, we said OD is equal to OB. They are both radi, because we say rad is a line which joins from the center to the circumference of a circle. Then after that, we were able to solve it using Pythagoras theorem, because we were told to calculate the length of the radi of the radius. Right. Now question 10. It's a bit It's a bit confusing, but it's also nice as well. Let's do question 10. All right. On question 10, let's read together. M is the center of a circle. Where is M? Here is M. M is the center of a circle. SVQR. Having equal chords SV. Where is SV? Okay. SV and QR. They are equal chords. Then RP and QP. RP and QP. They are tangents to the circle at R and at Q. Okay. All right. Then we are given that RPQ is equal to 70 degrees. Okay. So now, according to what you have written now, M is the center of the circle. Oh, what do we know about the center? We know that according to theorem number 3, angle as a center is twice the angle at a circumference, number 1. Okay. Now, we were also told that we have equal chords. SV is equal to QR. And now we're also told that RP and QP are tangent, which means these two lines are equal. RP is equal to QP. What's the reason of that? They are tangent from the common point. They are all coming from the same point P. Okay, which means this is an isosceles triangle. If these two are equal, which means this is an isosceles triangle, and these two base angles are equal, which means R2 is equal to Q2, because this is an isosceles triangle, RQP. Since we know that QP is equivalent to RP, they are tangent from the same point, and that automatically means R2 is equal to Q2. If these two are equal to each other, what is the reason for that? For them to be equal to each other, the reason is that angle opposite equal sides. Okay, we were just analyzing. We are not yet in the questions. All right, now let's go to the questions now. Question number 10.1. Question 10.1, they say, determine the size of R2. Where is R2? Where is R2? R2, it's here. So that one is already easy. We said that QP is equal to Q is equal to QR. Let's write it down. QP is equal to QR. Why is it that? Because they are tangents from common point. So they are tangent from the common point. So they are equal to each other. So what does this mean? If QP is equal to QR, is equal to RP, it means that this angle Q2 is equal to angle R2. So what's the reason? We can write that tangent from the common point, or we can just write that, since we have said earlier that QP and RP, they are equivalent to each other. Sorry. They are equivalent to each other. We now know that angles opposite equal sides, because we have already stated that these sides are equal. So now that's easy. So 2R2 is equal to, let me just start by saying that Q2 plus R2 plus 70 degrees must be equal to 180 degrees. What's the reason? It's because some angle of a triangle, okay, sum angle of the triangle is the sum angle. Sorry guys. So we started by saying that QP is equivalent to RP. Why? Because they are tangent from the common point P. Okay, so if they are equal to each other, that means that the base angles are also equal to each other, and the reason we say that angles opposite equal sides. Then now in triangle QRP, Q2 plus R2 plus that 70 degrees, it's gonna be equal to 180 degrees. We say that the sum of all the angles in a triangle, they add up to 180 degrees. Why? It's because sum of angles of a triangle. So now we are writing that. So since Q2 and R2, they are equal to each other, so we can say that R2 both because they are equal to each other. If q2 was x and x, which means they are the same to each other, they are like terms, so x plus x is 2x. But this case, let's just write this down. Okay, 2r2 is equal to 180 minus 70, it's 110 degrees. Then we divide by 2, we divide by 2, then we use our calculator, and we end up having r2 to be equal to 210, 5. Okay, we're gonna end up having 55 degrees. So basically our r2, our angle r2 is equal to 55 degrees. Then you get your 4 full marks. Wow. You see the marks, they just throw away marks. Okay, now let's just do the last two. Calculate the size of q1. Where is q1? This is our q1. We know this angle, we also know this angle. So now they are saying calculate the size of q1. Okay, do you see something here? Do you see that we have the center here? When you are writing Euclidean geometry, you can take your paper, you turn it like this, you turn it like this, as long as you'll be able to see what you're looking at. We have this line or this radius MQ. Do you see that one? MQ is the radius and MQ is perpendicular to this tangent. Do you see that? So if these are perpendicular to each other, which means Q1 plus Q2 is equal to 90 degrees. A line from the center to the circumference is a radius, and we are given the tangent QP. So since from the center to the tangent, which means the tangent is perpendicular to the radius. So if they are perpendicular to each other, which means they have to give us 90 degrees. So what are we going to write now down to answer that question? We're just going to write that Q1, angle Q1 plus angle Q2 is equal to 90 degrees. Why? Because tangent perpendicular to the radius. So what is our Q2? We say that Q2 is equal to R2. So Q1 plus 55 degrees is equal to 90 degrees. Then Q1 is equal to 90 degrees minus 55 degrees. Then we get 35 degrees when you use your calculator. Okay, now the last question. Determine the size of M2. Where is M2? Where is M2? Oh, okay. So that is where our M2 is. Now, we know something about M2. We know that M2 is here. And we know that MR is equal to MQ. They are both radius because they are radi, MR and MQ. They are radius because a line from the center to the circumference of a circle is a radi. So these two, if these two are equal to each other, which means Q1 and R1, they are equivalent to each other. Okay, always know that they are equivalent to each other. Q1 is 35, R1 is 70. So now let's just write that. So let's just say on our last question of the day, 10.3. On 10.3, we say that we saw that QM is equal to RM. Why? They are both radi. They are coming from the center, both of them. So what does this mean? If these two are equal to each other, this means that the base angle R1 is equal to Q1. Angle R1 is equal to Q1 is equal to 35 degrees. Why? Angles opposite equal sides. Since we know that the sides of them, they are equal. Let me just write something in reference here, that in triangle MQR, so that you can see that in triangle MQR, QM is equal to MR. Then we can state that they are both radius. So R1 and RQ1, they are both 35 degrees. So now we can say that angle M1 plus R1 plus Q1 is equal to 180 degrees. Why are they equal to 180 degrees? We know that sum angle of the of the triangle. What is our M1 is what we are calculating. What is our R1 is 35. Q1 is 35 degrees equal to 180 degrees. Then let's make M1 the subject of the formula. It's going to be 180 degrees minus 70 degrees, because 35 plus 35 is 70 degrees. Then our M1 is equal to 110 degrees. So that's our M1, guys. That's our M1. That's our M1. So that will be our answer. So this is Euclidean geometry, guys. It's so nice, it's so easy, it's so easy. You just have to know the theorems and be able to apply the theorems on your own. You must be able to apply the theorems on your own. Then you'll be able to survive this. Okay, again, we did the theorems, all of them. So today we just did these 2 examples. We hope to do part 2 as well, to do more questions on Euclidean geometry. So this is the Euclidean geometry, question 1, question 2. Did those 2 so that you can have a better understanding, and I believe you had a nice time with me. And I believe if you have any question, please do ask, so that we can be able to assist you in the future. Anytime when you ask us, we'll be able to assist you. Have a nice and a blessed night, and may God be with you till we meet again.